Welcome to our first podcast. This PowerPoint will review the following topics: subatomic particles, isotopes, and calculating average atomic mass. First, we start off with some modern atomic theory. So we know all matter is composed of atoms. Atoms cannot be divided, created, or destroyed in our ordinary chemical reactions. We refer to this as the law of conservation of mass. But we know now that these can occur in nuclear reactions. So when you have a nuclear reaction, you are actually splitting or dividing an atom. Atoms of an element have a characteristic average mass, and that is unique to that element. So each element has its own unique average mass, and that's one way that we can tell unknown samples is by looking at that mass. And lastly, atoms of any one element are going to differ in properties from atoms of another element. Often our elements are grouped by these properties, but they are going to be unique, and any atom of the same element will share those properties. Now we have our parts of the atom. So at the center we have the nucleus, and in the nucleus we have our protons and our neutrons. The protons have the positive charge, so remember P for proton, P for positive, and then our neutrons, as the name implies, are neutral or have no charge. Outside the nucleus is where we have our electrons, and those have the negative charge. Okay, this just breaks it down again. Our protons and neutrons are in the nucleus. Electrons are outside the nucleus, often referred to in an area known as the electron cloud. Protons are positive, electrons are negative. So in a neutral atom, you're going to have the same amount of protons and electrons so that those charges cancel out. As far as mass is concerned, I'm sorry, we're not there yet. We're still on charge. Neutral, as I just said on the slide before, I guess I was a little ahead of myself. I apologize. Our neutral atoms have no charge, again, because they have an equal number of positive protons and negative electrons, so those masses cancel out. Now, if you have an ion, which we'll get into later, those are atoms that do have a charge. But as far as just a regular neutral atom, no charge because of that equal amount of protons and electrons. This is where I was getting to, the mass of the subatomic particles. So protons and neutrons have just about the same mass, but our electrons are way smaller. So if you look at the exponents here, the protons and neutrons very similar. The electrons go or have a difference by about 24 to 28. And that's in scientific notation, so it makes a difference of about 2,000. We're estimating that number here. So we say electrons are much smaller. It would take about 2,000 electrons to equal one proton or neutron. So since that mass is so small, it's basically zero, so we just ignore it or consider it negligent. So whenever we're referring to anything dealing with the mass of the atom, we are completely looking at just protons and neutrons. Electrons do not affect mass at all. An analogy that I like to use, if you think about your hair, if you were to remove one piece of hair, that's really not going to affect your mass. So it's kind of the same idea. Electrons are so small that by removing one or adding one, you're really not changing the mass in any noticeable form. All right, so a review of a square from our periodic table. At the top, we have our atomic number in this diagram. Sometimes they're at the top, sometimes they're at the bottom. The way you know it's the atomic number is that it's always a whole number, and the atomic numbers go in order. So it'll start at 1 and go up from there. Our atomic number tells us our number of protons. So that's the most important thing. Atomic number is the number of protons. But because usually we're dealing with a neutral atom, it also tells us our number of electrons. Because as we discussed before, in a neutral atom, you'll have the same amount so that those charges will cancel out. At the bottom here, and typically it will be in a decimal form, is where we have our atomic mass. So that again is the protons plus the neutrons, but usually on most periodic tables this is going to be a decimal, and not because there's a fraction of an amount of neutrons or protons, but because it's an average of the different isotope masses, and that's something we're going to talk about shortly. So for now, just make sure you're able to understand that the atomic number is telling us the number of protons, and that tells us which element it is, because all elements have their own unique amount of protons. Okay, and here's just that again. So atomic number equal to the number of protons and electrons if it is a neutral atom. atomic mass, as I mentioned, is the number of protons plus the number of neutrons. We don't include the electrons because, again, their mass is so small. All right, to find the neutrons, you'll notice that we haven't really mentioned how to find the neutrons yet. We know the atomic number gives us our protons and electrons, but we don't, have a number just by looking that tells us our neutrons. So to find our neutrons, you take your mass minus your atomic number. So again, in these examples, the mass is a nice rounded whole number, but in real life, they won't be. So you'll just round the mass up or down based on the regular rounding rule. So if that first decimal is 4 or less, you're going to round down. 5 or higher, you're going to round up. So then you just take your atomic mass and subtract your atomic number or your number of protons, and that gives you your number of neutrons. So in this particular example, we have a mass of 16 with 8 protons. So 16 minus 8 is going to give you 8 neutrons. Now in this example, the neutrons is the same as the protons and electrons, but that is not always the case. Okay, so this is what I was alluding to before. It says, why is the mass written as a decimal if it's the protons plus the neutrons? So the number on our periodic table is the atomic mass, and that is the average of all of the naturally occurring isotopes of that element. So what is an isotope? Isotopes are atoms of the same element that have different masses because they have different numbers of neutrons. So you can actually have two atoms of the same element that have different amount of neutrons. And that is what creates these isotopes because it gives them a different mass because they have different amount of neutrons. So here's an example. Hydrogen with a mass of 1, so this little number after the dash, that's representing the mass. So hydrogen 1 has 1 proton and 1 electron, no neutrons, so it doesn't have anything attached, it's just this little proton here in the nucleus. So the mass is just 1 because there's no neutrons. Where hydrogen 2 does have a neutron, so 1 plus 1, that's how we're getting that mass of 2, and hydrogen 3 has 2 neutrons. Now if you look at the periodic table, and I'm probably getting a little ahead of myself in the slides, the mass of hydrogen is 1.0079. So that tells us that the hydrogen 1 is way more common to see than the 2 or the 3. Whatever the average mass is closest to, that's the isotope that exists the most frequently, and we refer to that as the abundance. So we would say hydrogen 1 is the most abundant or commonly occurring isotope of the 3. So again, this is a way that you will commonly see the isotopes written. So we have carbon as our example. Each one has that atomic number of 6 because the atomic number is always the same for a particular element. So if it's not 6 anymore, then it's not carbon anymore. But you can see at the tops that those masses are all different because they have a different amount of neutrons. But in order to be isotopes, they have to be the same element. So that's really important. Oh, here we go. Isotopes have a different number of neutrons. All right, so there are two terms that are commonly used as the same thing. Like you may hear someone say atomic mass or mass number. There is a slight difference, so we just want to touch on that. The atomic mass is that number on the periodic table, and that's the average of those naturally occurring isotopes. So it takes into account how much of each isotope there is, and it comes up with this weighted average. We're going to go over that in a minute. The mass number is just simply the protons plus neutrons in that particular isotope. So they are kind of used interchangeably, but there is a slight difference in the actual definitions of the terms. Okay, so just a little bit on that again. Mass number, protons and neutrons in the nucleus. So again, just adding up those protons and neutrons. So you can kind of go through this little chart on your own time and try to fill these in to make sure that you understand, given certain pieces of information, how to find the protons, how to find the neutrons, how to find the electrons, how to find the mass number, and then writing the isotope name would be the name of the element with that particular isotope's mass. So you may see an oxygen 15. That just means that we're dealing with the 15 isotope, not the usual 16. So just watch out for that when you're completing charts like this. The name should not necessarily be the mass from the periodic table, with the mass number that you get when you add those protons and neutrons. So it could be a different isotope than the most commonly occurring isotope, which is what we see closest to our weighted average. I'm just going to click through these. Hopefully you tried them or paused and tried them. And now you can just sort of check through your answers. Okay. All right, and then just slightly more on this atomic mass. Hopefully this is getting a little redundant for you. So again, that atomic mass is the average of these naturally occurring isotopes. So we are actually, I think it's the next slide, going to learn how to do that. But the example here, we have carbon 12, carbon 13, carbon 14. We can see how the neutrons differ. Well, carbon 12 is 98.89% found in nature, or has an abundance of almost 99%. So clearly that's a lot more than the other two. So carbon 12, when we're talking about carbon, is almost always the isotope that we're referring to. So if you look at the periodic table, carbon has a mass of 12.01, which is because, like we just said, it's most commonly found in the 12 isotope. So the mass on the periodic table is going to represent that by being closest to 12. Okay, so average mass, again, because in the real world we use large amounts of atoms and molecules, we use the average mass in calculations. So the way that we would find this average mass is to take the particular mass of an isotope and then look at the weight of that, and the way that we do that is by looking at that relative abundance. So if we look back to the last slide, that abundance is that percentage. So we are going to be making a weighted average by using those abundances. And those of you who took honors, you should have done this last year, hopefully. So to calculate the average atomic mass, this is a little example, so you can kind of pause and read through the top if you would like. But basically what you're going to do, is calculate the atomic mass by taking the percentage of isotope 1, multiplying that by the mass of isotope 1, and then adding it to the same thing for isotope 2, isotope 3, etc. So isotope 2, you would take the percentage, multiply it by the mass, and you do that for each one, and then you would add them all together. So you would take your abundances that you're given, but we have to put it into decimal form. So you're just going to move the decimal 2 spots to the left, or divide by 100. Like, you know, when you make a percentage, you always multiply by 100. Well, to take it out of a percent, you just divide by 100. So you move your decimal 2 spots to the left. So that is where this 0.9893 is coming from. You would multiply that by the mass that's given, and that would be your first isotope. So we might want to put like a bracket or a big parentheses here just to separate them. You do the same thing for each one. Now, something that gets mixed up a lot is if the percentage is less than 10. A lot of people forget that there needs to be a 0 here. So when you move the decimal 2 spots, it's going to be 1, 2, and then you would add in a 0. So that's why this is 0.0107, and then again you'd multiply that by the mass. Okay, so then you would just add all of those together, and again I like to use a parentheses here and here, then hit add and a parentheses here and here, like we have it up here, just to keep everything clear on your calculator. Make sure you're doing it correctly. So that is the end. There are some problems for you to try with this, so hopefully based on this tutorial here, you'll understand and remember how to do that, and you can complete the problems on the notes sheet. Thank you.